everyone, welcome to Module 3, the Safety and Robustness section. I'm adversarial, a chemical engineering student with a pre-law track.
And my name is Richard Bisher, a computer science and applied math student.
So what will we be learning today? First, we'll be going over robustness testing with FGSM, defensive countermeasures, then moving on to robustness testing with Gaussian noise, then moving on to distribution shifts, and lastly, but not least, the regulatory landscape.
To start off, let's talk about some key definitions. What does AI safety and AI robustness mean? Well, AI safety really just means ensuring that AI operates as intended. So this can mean on the technical aspect, making sure that our error detection for our algorithms is up to date, but on the ethical side, that it also aligns with positive human values, including ensuring that we're taking the most responsible and safe decision. AI robustness, on the other hand, refers to maintaining the performance of our algorithm within any sort of situation. So essentially, reliable performance under situations like input fluctuation, so noisy or manipulated data, distribution shifts, and thirdly, if there's operational stressors, for example, of the hardware or if there's cybersecurity failures within the system.
Now let's get into robustness testing with FGSM. FGSM stands for Fast Gradient Sign Method. But what does that mean? Essentially, think of an attack on an algorithm using gradient ascent to generate adversarial examples. Think of it as adding a sort of invisible to the human eye fog over an image, making it very difficult for an AI system to detect what is exactly going on. For example, we could have a scenario in which, as with the dog, you could detect what type of dog it is. But then you add all of this noise into it, causing people to have some errors.
Now, let's take a look at what this looks like in a code format. This is what the notebook in the Google Colaboratory will look like when you first enter. And in the start, we just go over some core definitions of what AI safety and AI robustness means, just like we had gone over initially. But I want to bring your attention into the technical overview, where the first technique we'll be going over is the fast gradient sign method, FGSM. However, there are some other technical methods that you could use, including robustness testing with noise injection, which we also will be doing in the notebook, distribution shifts, and as well as uncertainty quantification and failure prediction, and some more information is provided here. But first, let's go over how you would actually implement a fast gradient sign method, again, which is called FGSM. So step 0 would first mean to set up and import all the necessary libraries. So you can see we're using Torch Vision, OS, Matplotlib, and NumPy, just to name a few, which are just libraries that are very important to help us visualize and work with the numbers in this notebook. So we just run that cell. Then step 1 relates to actually loading the data and building the model. Here, we are using the MNIST dataset, which is a widely used benchmark for image recognition and machine learning. And the idea is that it uses handwritten digits from 0 to 9, and we're going to use that to classify and train our model. So essentially what we're doing here is allowing the machine learning model to be built, and we're going to be teaching it on exactly how to detect certain numbers. So the first step would be to actually define that transform and load in the data sets, as well as the actual images of the numbers, as in load full data sets. But for the sake of the tutorial, and if you want to get a quick peek into how the model is performing, you can also use just like 100 of the samples or like 1,000 of the images in case you would want to do so. So I'm going to quickly add that in. So I'm just going to make it called like train data set. And that's going to be equal to the subset of the full train data set. And we're going to be this in a list of range 100. So this is for the train set, and now we have to do the same thing for the test data set. So test data set would be equal, to the subset of the full test data set, again, which will be in list of range 100. And this is just for the sake of time, but this would just ensure that we're only using 100 images. After that, we actually load in the pre-made model and modify one of the layers. And then we just want to check that the model checkpoint actually exists and that we can access the data. After that, the model will be trained. And then we will save the trained model. And this should be updated to 100 if you guys caught that error. So let me go ahead and run this cell. The green check mark means we're good to go. And you can see the output. This is what the model looks like. So it has different layers. So layer 1, layer 2, layer 3, and then it even deep dives into what specifically those hyperparameters look like. Step 2 would actually be to now write the attack function. So here we're going to define a method that takes on the image, the epsilon value, and the data gradient value. And so what we need to do here is actually make sure that we enter what the perturbed image is going to look like. So this is what happens when the attack quote unquote occurs. So for that, I'm just going to define a variable called perturbed data. And I'm going to set that equal to the actual image plus the epsilon value, which is, the magnitude of the attack times the signed gradient. Sorry, I misnamed this variable. Let's call that perturbed image. So now let's run this cell. And now we've defined a function to actually do the attack. Step 3 would actually be displaying the images. So here is a really simple method that is able to plot the images so that we can see it. And then specifically, I make sure that we choose one image from the test data set so that we can actually see what it looks like. So let's go ahead and run this cell. So again, this is just a function to do so. Next, we're also going to predict and calculate the loss. So this is important to make sure that we're evaluating our model and understand how exactly it looks. And so here, we're going to enter in the exact loss function that you would want to be using. So for that, we're going to use something called a cross entropy loss, which is a way to measure this. So we're going to set the loss is going to be equal to the model dot cross entropy loss, and this is going to take in the outputs as well as the labels. Then we're going to actually generate the adversarial images. So again, this uses the attack that we defined earlier, and we're setting a magnitude level. I want to bring your attention to this epsilon value because again, that actually determines like the magnitude of the attack that you're going to be doing. So feel free to play around with that because it can be really interesting to see what happens. And I'll be running a couple examples. So let's go ahead and run this. And then we get our original and adversarial prediction. And lastly, we're just going to visualize our output. This is from a previous run, so let's go ahead and run this. So we can see that the noise is actually added to the image, which again can really confuse the model if it's trying to learn on certain types of data. Now let's quickly go back and change the epsilon value to see what occurs. So let's see what happens when we increase that epsilon value. Feel free to pause and really think about what your prediction would look like. So let's rerun this. And now let's visualize the image. So you can tell that the noise is very much increased and it looks even more blurred than usual. But now let's go ahead and decrease that epsilon value. Running that cell and visualizing the image. You can see that it's a lot less granular and more clear. So that is essentially a quick run through of how to do an FGSM. And for a quick recap, it computes the gradient of the loss with respect to the input image. It takes the sign of that gradient to determine the direction to actually alter each pixel. It adds a small controlled amount, which we have defined as epsilon of noise in that direction. And then it creates a new adversarial image that looks scarily identical to humans, but it tricks the model actually into producing a wrong prediction. All right, so that's what it looks like to be in the notebook.
Hello, now let's look at some defensive countermeasures. Well, what can you do? You can actually train your model with adversarial training. Essentially, you're giving it these perturbed images and examples we saw in the notebook and helping it improve upon understanding what it's doing incorrect to help improve its classification of both clean and adversarial inputs. But we could also do something called randomized smoothing. We essentially certify robustness via noise injection, with the goal being to provide guarantees that the model's predictions won't change under small input perturbations.
A third technical method that we could use would be to robustly test with Gaussian noise. And so essentially this simulates what a real world input of noise would look like. And you can think of it very similar to an FGSM where it's going to be convoluting like the input or our actual data. So the steps to actually use this method would be one, to like inject the noise into the test data, which again would confuse and add additional complexity which doesn't need to be there. And second, you would then measure the performance, and ideally, or as expected, you'd be seeing a drop in the performance or the accuracy. And the goal here is to essentially ensure that the model degrades gracefully or as expected, because with an increase in noise, you would expect that the data or the data's classification would degrade its accuracy and its ability to evaluate what's correct. That ability would decrease. So now let's look at what this would look like in a code setting. Hello everyone, I'm back to talk about how you would go about implementing robustness testing with Gaussian noise. Similar to the first example, step 0 would be to import the proper library, so using things like matplotlib, numpy, and torchvision to ensure that we have the necessary tools to manipulate our images as well as data. Let's go ahead and run this out. When you see that green check mark, you know that we were able to compile with no errors. Step 1 would now be to define the image transforms and load the test data. So you can see we define this variable called transform, and then also make sure to resize our image as well as add grayscale. Again, similar to the first example, we're only going to be using the first 100 images, and this is only for speed, but it's important to note that the more examples that you're able to add, or data points you're able to add, it will be sure to increase your accuracy. And that is important to ensure that we're building a model that is very robust. Let's go ahead and run this. Step 2 would be to actually go ahead and load our model and ensure that we are ready for testing. So in this code, what we're doing here is adding a checkpoint path and then actually loading that and allowing our model to evaluate. If this were able to compile correctly, we should be able to see that our model is loaded and we are ready for testing. As you can see in the output, the path has been printed and that line indicating that we are ready to go has been printed, meaning our model is loaded and we are ready for testing. Similar to the first example, and now you can probably tell that there are a lot of similarities in this process of adding noise. We're going to define a function called add Gaussian noise to actually ensure that we're adding the perturbation to the image. And the way we're going to do this is by adding a variable called noise. And we're going to set this into a random, using the random function, as well as adding the mean of the value. After that, once we've created the noise, adding it to the image and then actually returning that noisy image. Step 4 would be to actually visualize and test on the original image versus the noisy image. So the idea here is that we can predict on our clean image, and then also we have a prediction for our noisy image. But there is an important step, which is actually to call our method that is used to create that noise. So let's go ahead and do that. Now we should be able to print the clean prediction, noisy prediction, and the true label to ensure that we are doing this correctly. Lastly, we can visualize this side by side by plotting this in an image, and we can see the difference. As you can tell, that our predictions are very bad because, again, we're training on a very low amount of examples, but you can clearly see the additional noise, which is the Gaussian noise that was added. As a bonus, feel free to evaluate the accuracy under different values of increasing noise, and I've added that code here. And also, feel free to also plot this to see how the accuracy looks like for these different noise levels. That concludes this segment, but to quickly note, please feel free to also read through our value alignment and societal impact section, as well as the regulatory landscape, which Matthias will be touching on in a little bit. Thank you. Hello, everyone. We hope you enjoyed the notebook section, and now we're ready to discuss the next technical method in this module. We will be discussing distribution shifts, which relates to a training dataset and testing dataset mismatch.
Okay, so let's dive into it. What do we mean exactly with this? Well, it's essentially a way of testing for robustness, right? Think of splitting your data up in two. One is used for the training, the other is using for the testing. We split it up in this way to make sure that if we have any errors, we can understand where the errors are coming from. Is it perchance an image that was incorrectly generated? Or is it an error or bias within the data we have? And there's different metrics we can use this, such as the accuracy drop or uncertainty quantifications. Hello everyone, we'll now be digging into the regulatory landscape. There's a lot to say about this, however, we'll be digging into three main areas of the world: the EU, the US, and China. These are all very interesting case studies of how to interact with AI. For the EU, we have the AI Act of 2023, which is essentially a way of creating a tier list, if you will, of risk within AI testing, right? Something high risk would be having no robustness testing, having no human oversight, right? However, that would not quite be on the level of prohibited. It's just not the smartest idea. On the other side of the pond, you have the US executive order signed by Joe Biden in 2023, which developed the NIST standards and required red teaming for all AI models. However, on the state level, we have more to see. For example, AB 2013, signed by Gavin Newsom, requires that these AI models share what data they're trained on. On the other hand, you also have SB 942 within California, which requires that any AI model has a system of developing and understanding if what they generate is created by AI. Then on the other hand, you have China, which requires human in the loop whenever testing with AI and has a specific focus on reliability.
All right, everyone. This is Richa.
And this is Matisse.
Signing off for Module 3. Thank you so much.
Bye.